There is something strange about the way discovery actually happens. Not the way it's described afterward, with its clean sequence of observations and conclusions and names, but the actual thing, the lived thing, which tends to be slower and more confused and involves a great deal of sitting with numbers that don't quite add up, waiting for a question to form that fits them. That's where this begins, not with an answer, not even with a question, just the numbers. Welcome. If you found yourself here, lying down, ready to let something quiet move through your mind before sleep, this is the Sleepy Physicist, and I'm glad you're here. Tonight we're going somewhere that took science decades to even name. If you'd like to be part of what makes this possible, you can visit the channel page. There's something there for those who want to go a little deeper. But for now, just this, just the dark, and what's moving through it. Sometime in the 1970s, astronomers began noticing that galaxies in a particular part of the sky were not moving the way the model said they should. This was not an alarm. Science is full of small discrepancies. Instruments misbehave, calibrations drift. There are always candidates for blame. You write it down, you move on, you come back to it later. But some of these astronomers came back to it. The data was simple, in the way that the most unsettling things are often simple. Galaxies were moving. That was expected, and the universe was expanding, carrying everything outward the way dots on a balloon move apart when you inflate it. But some galaxies were also moving in another direction, on top of the expansion, with a velocity that didn't belong to the inflation of space itself. A residual. A remainder after the expected motion had been subtracted out. The word for this, in the language astronomers use, is peculiar velocity. Peculiar not in the sense of strange, though it would prove to be, but in the technical sense of belonging specifically to the object itself, not borrowed from the overall drift of the cosmos. These galaxies had peculiar velocities. And the peculiar velocities were pointed, many of them, toward the same region of sky. For years this sat in papers, in conference discussions, in the margins of calculations that were primarily about something else. It wasn't ignored exactly, it was pending. Science accumulates a large number of pending things. Most of them resolve into mundane explanations. A few of them don't. In 1973, a group of researchers published a map of galaxy velocities that showed the motion more clearly than it had been shown before. The flow was visible, not dramatically, not in a way that anyone looking at the map for the first time would necessarily notice, but it was there. Hundreds of galaxies across a wide region of sky, all moving towards something that the map couldn't show because the map could only measure what was visible. What was pulling them wasn't visible. This is the part that takes a moment to absorb. The thing that was causing the motion was hidden. Not hidden because it was small. Hidden because of where it was, behind a dense region of dust and gas belonging to our own galaxy. A curtain drawn across a section of sky so thick with interstellar debris that light from whatever lay beyond it could not pass through. Astronomers eventually named this region the zone of avoidance. Not a dramatic name, functional. This is the part of the sky we cannot see because our own galaxy is in the way. And the thing pulling thousands of galaxies through space, or including ours, was sitting apparently just behind it. There's something that takes a while to settle about this. That a force operating at the scale of hundreds of millions of light years, a force that would eventually be understood as one of the largest gravitational influences our instruments have ever measured, was, for most of scientific history, simply missing from the picture. Not theorized and unconfirmed, not suspected and unverified. Absent, not yet a question. It is hard to know how to think about the period before a discovery. We tend to look back at it from afterward, which means we import all the knowledge we now have into the past and imagine that the people in it were somehow failing to find what we now know is there. But that isn't how it works, or at least it's not how it felt from inside that time. Inside that time, there were just numbers, and a faint unease that not everyone shared, because not everyone was looking at the same data, and not everyone who was looking at it thought the unease was worth pursuing. The ones who thought it was worth pursuing, it would take them years, more than a decade in some cases, between the first inklings and anything resembling a claim that could be defended in print. That's a long time to sit with the feeling that something doesn't fit. A long time to trust a discomfort before you have the language for it, which is maybe the most honest description of how science sometimes moves. Not forward in steps, but sideways in the dark, hands out, trying to find the shape of something by what it isn't. The numbers were real, the motion was real, the thing causing it was real, only the word was missing. And before a thing has a name, it exists in a particular kind of silence, present in data, present in the motion of galaxies crossing hundreds of millions of light years of space, and somehow still, in every practical sense, not quite there yet. There's a version of science that gets talked about as the series of moments, the discovery, the paper, the name. But the longer version, the one that happens in real time, is mostly made of the space before those moments. The years when the question hadn't fully formed, when the data sat in notebooks and the motion sat in the sky, and no one had agreed on what they were looking at or whether it deserved a name at all. That period, the period this chapter inhabits, lasted roughly a decade, depending on where you decide it starts. And somewhere, in the same sky that astronomers were mapping with their catalogues and their redshift measurements, something was already pulling, already had been, for longer than any human counting. The name would come later. For now, there was just the pull and the silence around it and the slow work of noticing. In the next chapter, we stay in the ordinary for a while, the unremarkable night sky, before anything in it announces itself as strange. On most nights, if you go outside and look up, nothing about the sky suggests anything unusual is happening. That's not a poetic observation, it's just true. The stars are where they were last night. The familiar patterns, Orion, the Dipper, the faint smear of the Milky Way on a dark enough evening, hold their positions the way they always have. The moon moves. Planets drift slowly against the fixed background. Everything else stays put. The sky as a human experience is one of the most stable things available to us, and underneath that stability, at this moment, our galaxy is moving through space at roughly 600 kilometers per second toward a region we cannot see. Those two things are both true simultaneously. They don't cancel each other out. The stability is real. The motion is real. They simply exist at scales so different that neither one disturbs the other. The stars you can see from Earth number somewhere around 5,000 on the clearest possible night from the darkest possible location with no moon. Most people in the most places see far fewer than that. Light pollution reduces the visible sky considerably. A typical city night might offer a few dozen stars, if that. But those few dozen, or those 5,000, they are all inside our galaxy. They are neighbours in the cosmic sense. The closest of them, Proxima Centauri, sits about 4 light-years away. The farthest visible to the naked eye, depending on conditions, might be a few thousand light-years out. The galaxy itself extends roughly 100,000 light-years across. The Great Attractor, the thing pulling the galaxy, sits somewhere between 200 and 250 million light-years away. The stars you can see with your eyes are, in relation to that distance, essentially here. They're in the same room as you if you imagine the pull as something happening outside the building entirely. There is a kind of stillness that comes from understanding Fail rather than just reading it. It doesn't arrive quickly. It builds slowly over repeated encounters with the numbers, and even then it comes and goes. You read that something is 100 million light years away and the mind acknowledges it and then quietly sets it down, because there is nothing useful to do with it in the moment. Nothing in ordinary experience maps onto it. That might be the right response, actually. Not to force comprehension, but to let the number sit beside you without demanding that it become something you can picture. The sky on an ordinary night doesn't ask you to picture it differently. It looks the same as it did before you knew any of this. The motion doesn't show, the pull doesn't announce itself in the visible light coming down through the atmosphere. It is happening regardless. Astronomers in the early 20th century didn't know the galaxy was one of many. The prevailing view, well into the 1920s, held that the Milky Way was essentially the whole of the universe, a large disk of stars surrounded by empty space. The spiral nebulae scattered across photographic plates were thought by many to be objects within our galaxy. Gas clouds, perhaps. Young solar systems forming. Then Edwin Hubble measured the distance to one of them. The Andromeda Nebula, what we now call the Andromeda Galaxy, turned out to be nearly 1 million light-years away. The measurement was made using a type of variable star whose brightness cycles at a predictable rate, which makes it possible to calculate how far away it must be to appear as dim as it does. The calculation put Andromeda far outside any reasonable boundary for the Milky Way. The universe, in the span of a single measurement, expanded, not physically, conceptually. The map grew to include structures that had been in the data all along, waiting for the right instrument, the right method, the right question. That pattern, the map growing to accommodate something that was already there, would repeat. It always does, it seems. The ordinary sky sits above a planet that is orbiting a star. The star is orbiting the center of a galaxy. The galaxy is a member of a small local group of galaxies. The local group is part of a larger cluster. The cluster is part of a supercluster. And the supercluster, the entire structure, 100,000 galaxies or more, is moving. Each layer of this nesting was discovered separately. Each one required new instruments, new methods, and a willingness to accept that the previous boundary was not the final one. The person who first looked up and saw the ordinary sky had no way to know any of this. Neither did the person a generation later, or a century later. The knowledge accumulated slowly across many lifetimes, and it is still accumulating. The current picture is not the final picture. That seems worth saying plainly. The motion is so constant, so indifferent. The motion is so constant, so indifferent to observation, so entirely unaffected by whether anyone is watching or measuring or naming it. The galaxy moves toward the attractor whether or not there is an astronomer with a spectrograph pointed at a distant galaxy cluster, whether or not there is anyone lying awake at night thinking about it. The motion belongs to the physics, not to the understanding of it. That distinction between the thing and the knowing of it is easy to lose track of in science communication, where the discovery tends to get told as if it is the same event as the phenomenon. The Great Attractor was not created when it was named. The pull was not initiated when astronomers confirmed it. It was there before the notebooks, before the telescopes, before the first careful person looked at a galaxy's velocity and thought, "This doesn't fit." The ordinary sky held it the whole time. It still does tonight, above wherever you are. The stars in their usual places, the atmosphere bending their light slightly as it always has. Nothing in the visible scene suggesting that everything in it is part of a slow, enormous motion towards something hidden behind dust, 200 million light-years away. It seems sometimes that the most significant things are the ones that look most like nothing from the outside. The dust that hides the attractor is not metaphorical dust. It is real, particles of carbon and silicate distributed through the plane of our galaxy. dense enough in certain directions to absorb and scatter visible light almost completely. What lies behind it is not invisible by nature. It is invisible from here and for now. That particular problem, the zone of avoidance, the curtain of our own galaxy drawn across a crucial section of sky, sits at the centre of the next chapter. Motion is not always visible. You know this already without thinking about it. You've sat on a train that was moving so smoothly you only knew it by the window, the platform sliding away, the buildings rearranging themselves outside the glass. The motion was real. The stillness you felt was also real. Both were happening at once, and neither one was lying to you. The galaxy moves like that. Not metaphorically. The comparison isn't decorative, it's pointing at something specific, the way a thing can be in genuine motion and yet feel from inside it completely stationary. The train analogy breaks down eventually, as all the analogies do, but the basic physics it's pointing at doesn't. An object in uniform motion has no internal signal of that motion. Nothing inside it vibrates differently. Nothing feels pushed or pulled. You would need something outside, a window, a reference point, another object not moving the same way, to detect it at all. Astronomers needed the same thing. To measure how a galaxy is moving, you need something to measure it against. The universe offers one reliable reference: the expansion of space itself. Everything in the cosmos is, on average, being carried outward by the stretching of space. The rate of this expansion, called the Hubble flow, is not perfectly uniform, but it is predictable enough to serve as a baseline. If you know how far away a galaxy is, you can calculate how fast it should be moving away from us due to expansion alone. Then you measure how fast it's actually moving. The difference between those two numbers is the peculiar velocity, the part of the motion that doesn't belong to the expansion, the residual, the leftover. In most directions, peculiar velocities are small, random. A galaxy moving slightly faster than expected here, slightly slower there. Statistical noise, essentially, caused by local gravitational influences pulling things around at relatively short ranges. But in one part of the sky, the peculiar velocities were not random. They were pointed. Hundreds of galaxies spread across an enormous region of space, all moving in the same direction, toward a specific location, at speeds that local influences couldn't account for. Something was pulling them, something with enough mass to reach across hundreds of millions of light years and leave a measurable mark on the motion of entire galaxies. Feel the floor beneath you for a moment, not metaphorically. Actually register it, the pressure of the surface against your back or your side wherever you're lying. That pressure is gravity. Earth's mass-curving space-time around itself, holding everything on its surface in place. You feel it as weight, as the particular heaviness of your own body against whatever is supporting it. Now consider that same force scaled up, not to the mass of the Earth, not to the mass of the Sun, not even to the mass of the galaxy, but to the mass of something larger, a concentration of thousands of galaxies, plus the dark matter surrounding them, plus the vast structural filaments connecting them. A total mass so large that its gravitational influence doesn't drop to zero at the edge of our local group, or at the edge of our supercluster, but reaches measurably across 200 million light-years of space. You cannot feel that pull the way you feel the floor. The force gradient across the diameter of your body, the difference in pull between your head and your feet, is so vanishingly small it has no physical meaning at the scale of human tissue. It registers nowhere in you, but it registers in the data. The galaxies feel it. Not feel it the way you feel weight. No, perhaps that's not quite right. Galaxies don't feel anything. but respond to it in the precise physical sense. Their paths through space are curved by it. Their velocities carry an imprint of it. The mass at the centre of the attraction has written itself into the motion of everything within its reach, the way a heavy object placed on a stretched fabric writes itself into the slope of the surface around it. Our galaxy is on that slope, has been for longer than the Earth has existed. When astronomers began mapping peculiar velocities systematically in the late 1970s and through the 1980s, the picture that emerged was not simple. It wasn't a single arrow pointing at a single source, it was a flow, a word that turns out to be more accurate than pull, more accurate than fall, a large-scale coherent motion across a region of space containing thousands of galaxies, all drifting in the same general direction. The region they were drifting toward was in the direction of the constellations Centaurus and Hydra, in the southern sky mostly, dense with distant galaxies in the parts that were visible, and then, across a wide band obscured Obuisen, the dust and gas of our own galaxy's plane blocking the view completely. Whatever was causing the flow was partly visible. Clusters of galaxies in Centaurus, concentrations of mass that clearly contributed, and partly hidden. The visible mass wasn't enough. The calculations kept coming up short. There had to be more behind the zone of avoidance adding its gravity to the sum. This was the inference that took years to harden into something resembling consensus. The flow was real, the visible mass was insufficient, and something unseen was contributing to the pull. The name Great Attractor was used for the first time in a 1987 paper. 7 astronomers, a collaboration that became known informally as the Seven Samurai. Not because the name was poetic, but because the thing needed something to call it in print. A placeholder in some ways, a label attached to a region of space and a gravitational influence, not to a single identified object. The name stuck. Names tend to, once a paper has been published. There is a particular quality to the moment when a measurement stops being an anomaly and becomes evidence of something real. It doesn't happen all at once. The data accumulates across different research groups, different instruments, different approaches, peculiar velocities mapped by redshift surveys, galaxy counts compared across different regions of sky, independent analyses converging on similar answers. The convergence is not dramatic from the inside. It looks like a slow accumulation of agreement. One group's result consistent with another's. A new survey filling in a gap. An analysis using a different method landing in roughly the same place. By the late 1980s, the flow was established well enough that most working cosmologists accepted it. The source was not established, not its precise location, not its total mass, not its structure. But the effect was real. Thousands of galaxies, our own among them, moving towards something behind a curtain of dust. The velocity our galaxy carries toward the attractor, roughly 600 kilometers per second when you add our motion relative to the local group, the local group's motion relative to the larger flow's participation in the overall pull, is not a speed you can feel. It doesn't register in your body, doesn't affect the weight of your limbs against the mattress or the pressure of the pillow against the side of your head. But it is the speed you are actually moving through space right now. 600 kilometers every second towards something that has no visible face. The data established the motion long before the source was understood. That order, effect first, cause later, cause still only partially understood, is how this particular piece of science actually went. Not a clean sequence from observation to hypothesis to confirmation, but something messier and slower and more honest about the limits of what instruments can reach. The dust is still there. The zone of avoidance has not cleared. What lies behind it has been partially mapped now in frequencies of light the dust cannot block, and what those maps found is the subject of a later chapter. For now, the velocity is enough, the pull leaving its mark on motion, the effect outlasting for years any clear understanding of its source. The numbers were real before anyone knew what to call them. The motion was happening before anyone had the right question to ask about it. That's where the next chapter goes, into the dust itself, not what's behind it, just the dust. Way sediment sits at the bottom of still way sediment sits at the bottom of still water. Distributed, patient, present in concentrations that vary from place to place but never fully absent along certain lines of sight. It is made of small things, grains of silicate, carbon particles, some of them smaller than the wavelength of visible light, which is part of what makes them so effective at blocking it. When a photon of visible light encounters a grain that is roughly its own size or smaller, the interaction is not a clean collision. The light is scattered, redirected, sent off at an angle that has nothing to do with where it was originally going. Enough of these interactions, across enough grains distributed across enough light-years of galactic plane, and the light that started at a distant source simply does not arrive. Not absorbed entirely in most cases, scattered, redirected so many times, across so many grains, that it no longer carries any directional information about where it came from. The band of sky where this happens most completely runs along the galactic equator, the plane defined by the flat disk of the Milky Way, which we see edge on from our position inside it. In the night sky, this appears as the dense, cloudy stripe of the Milky Way itself, the concentration of stars and gas and dust that marks the direction of the galactic center and its surroundings. Early sky surveys mapped galaxies across the whole sky, or tried to. The maps have a consistent feature, a band of emptiness running along the galactic plane where almost no galaxies are catalogued. Not because there are no galaxies there, because they cannot be seen through the dust. This is the zone of avoidance. The name was used practically, as a note to observers. This region will not yield results. Do not waste telescope time here. The dust column is too thick for the visible light to penetrate. The zone is not perfectly opaque everywhere along its length. The density of dust varies. There are windows, narrow regions where the column is thinner and some light gets through. But in the directions most relevant to the Great Attractor, the coverage is substantial. The galactic plane in the constellation Centaurus, in Norma, in parts of Hydra, these are among the denser sections, the areas where the dust sits heaviest between us and whatever lies behind. To understand what dust does to light, it helps to understand what light is doing in the first place. Light from a distant galaxy travels for hundreds of millions of years across space, which is for all practical purposes empty. The intergalactic medium contains so little matter that it presents almost no obstacle to a photon crossing it. The photon arrives at the edge of our galaxy having lost almost nothing to its journey. Then it encounters the disk. The disk is not empty. It is threaded with gas and with dust, the material between stars, denser near the plane, thinning above and below it. A photon travelling from a galaxy that happens to lie in the same direction as the galactic plane must pass through this material to reach a telescope on Earth. Depending on the wavelength of the light and the thickness of the dust column in that particular direction, the photon may or may not survive the crossing in a form that carries useful information. Visible light, the wavelengths human eyes evolved to detect, does not survive well. The grains scatter it too effectively. Infrared light, longer wavelengths, lower energy, fares better, passing through the dust with less disruption. Radio waves pass through almost entirely unimpeded. X-rays, depending on the energy, can penetrate regions that would be completely opaque to optical telescopes. This is why the zone of avoidance is not equally opaque to every instrument. It is a zone of avoidance specifically for optical astronomy, for the wavelengths that filled the early catalogues and the photographic plates. For other instruments, it is merely difficult, or in some cases not difficult at all. The Great Attractor was hidden, in other words, from a particular kind of looking, the kind available for most of the history of the field. There is something worth sitting with in this. The dust did not know it was hiding anything. It has no intention, no arrangement, no relationship to the object it conceals. It predates human astronomy by several billion years. It was formed from the remnants of old stars distributed through the galaxy by stellar winds and supernova shockwaves, settling into the disk over timescales that dwarf anything in the history of life on Earth. That this dust happened to lie, from our particular vantage point inside the galaxy, between us and one of the largest gravitational structures in our cosmic neighbourhood, this is not a design. It is geometry. The zone of avoidance exists because we are inside the disk looking outward, and the disk has material in it, and some of what we might want to see happens to lie on the other side of that material. If Earth were positioned differently within the galaxy, above the plane, say, looking down at the disk rather than through it, there might be no zone of avoidance at all. The attractor would have been visible to early optical surveys. The flow might have been explained decades earlier. But Earth is where it is. The dust is where it is. The geometry is what it is. And perhaps that observation goes nowhere useful. Perhaps it is just a fact about contingency that doesn't resolve into anything. What the dust does physically is also called extinction, the reduction in brightness of a light source due to the absorbing and scattering material between the source and the observer. Astronomers measure extinction in magnitudes, a logarithmic scale of brightness. A source behind one magnitude of extinction appears about 2.5 times fainter than it would without the dust. 2 magnitudes, about 6 times fainter. 3 magnitudes, about 16 times fainter. In the densest parts of the zone of avoidance toward the Great Attractor, the extinction in visible light runs to tens of magnitudes in some directions. A galaxy that would be easily detectable without the dust becomes effectively invisible, not because it emits less light, but because almost none of that light arrives in a form that optical instruments can use. This is a calibration problem, a measurement problem, an instrumental problem, the kind of problem that changes as instruments improve and new wavelengths become accessible. It does not change the dust. The dust remains exactly as it was. Extinction is the word. The dust extinguishes light the way, in a much smaller and more familiar sense. Fog extinguishes the lights of a city seen from a distance, not destroying the source, not altering it, simply reducing what arrives at the eye to something too faint or too diffuse to be read clearly. That is the central action here, not destruction, reduction. The distant galaxies behind the dust are luminous. They are massive. They are, in some cases, among the largest structures in the local universe. They emit light continuously in all directions, including toward us. Very little of it arrives. The dust sits between, as it always has, doing what dust does, scattering, redirecting, extinguishing, indifferent to what it conceals, indifferent to the telescopes on the other side of it, indifferent to the centuries it took the people holding those telescopes to find other ways of looking. The dust is not dramatic, it does not glow, it does not announce itself. It simply sits in the plane of the galaxy, patient and distributed, and lets the infrared through, which is where the next chapter eventually goes, though not yet. There is a particular kind of stillness that comes just before sleep, where the body is mostly stopped and the mind is still turning something over, not urgently, just rotating it slowly in the dark the way you might turn a smooth stone in your hand without really looking at it. And in that stillness, if you pay attention to it, there is something underneath the quiet that is harder to name. A sense, maybe, not of peace exactly, but of suspension, of being held in place by nothing you can point to. You are not held in place. You are moving right now as you lie there, at a speed that would cross the continental United States in roughly 5 seconds, and the direction of that motion is towards something you have never seen and cannot see, and that has no name beyond the functional label someone attached to it in a scientific paper published the year before some of you were born. That is not a metaphor. That is the actual physical situation of your body at this moment. Motion at this scale is not something the body reports. There is no sensation attached to it, no inner ear signal, no pressure against any surface of you that would suggest anything other than stillness. And yet the stillness is in some sense an illusion. Not a false one, not a lie the body tells, but a real experience of a relative state. The way the stillness of a room is real, even when the building it belongs to sits on a planet spinning at 1,000 kilometers per hour at the equator, orbiting a star at 30 kilometers per second, the star itself moving within the galaxy moving within its local group, the local group moving within the larger flow. Each layer of motion is real. Each layer of stillness is also real. They coexist without contradiction because motion is always relative, always measured against something else, and the something else you live inside of is moving with you. The walls and the floor and the air in the room all carried along in the same flow, so that relative to any of them you are perfectly still, and relative to the cosmic microwave background radiation, the oldest light in the universe, the faint thermal glow left over from a time before galaxies existed. You are moving at roughly 600 kilometers every second in the direction of a region of sky in the southern constellation of Centaurus. 600 kilometers per second. Sit with that number for a moment, not to understand it, not to translate it into something more manageable, but just to let it be in the room with you. It is the speed of your body right now, the speed of the bed beneath you, of the building around you, of the ground the building sits on, of the entire planet, of the entire solar system, the entire galaxy, the entire local group. All of it moving together, carried in a flow that has been running for longer than the Earth has existed, toward a gravitational center that our telescopes could not see directly until relatively recently, and even now cannot see completely, because the dust of our own galaxy still sits across part of the view. You are falling towards something hidden. You've always been falling toward it. Every person who has ever lived on this planet was falling toward it, and none of them could have known, because the instruments needed to detect the motion didn't exist yet. And even now that the motion is confirmed and measured and accepted, the falling continues exactly as it did before, indifferent to the knowing. There is a question that surfaces here, if you let it. What does it mean to fall towards something you cannot reach? The universe is expanding. The space between our local group and the Great Attractor is not static. It stretches, continuously carried outward by the same expansion that Hubble's measurement first made legible. The attractor pulls, the expansion pushes. The net result is motion toward the attractor that is real and measurable, but that may never close the distance because the distance itself is growing, has been growing, is growing now, and at large enough scales the expansion wins over gravity, carries things apart faster than gravity can draw them back together. So there is a possibility, not certain, but real, that the falling never arrives, that the motion is genuine and the destination unreachable, not because of any obstacle between us and it, but because the fabric of space between us is being continuously produced. New space emerging between old positions, keeping the gap open even as the velocity carries us toward it. This is not a tragedy. It takes a moment to be sure of that, to feel it rather than just assert it. But it isn't. It is more like the way a river moves towards the sea without the river being concerned about the sea, without the motion requiring any particular outcome to be real. The motion is real, the pull is real, the falling is real. What happens at the end, whether there is an end, whether the expansion eventually wins entirely, none of that changes what is happening now, which is that you are in motion, the galaxy is in motion, thousands of galaxies are in motion, all of them responding to the same gravitational signature, all of them falling in the technical and the almost poetic sense of that word toward the same hidden place. I think there is something genuinely clarifying about this, and that's a personal observation, not a scientific one, but it seems worth saying. The idea that the most significant motion you will ever participate in requires nothing from you, cannot be felt, cannot be unstopped, and has been underway since before the first single-celled organism appeared in the warm, shallow water of a young Earth. Participation here is not optional and not chosen. It is simply the condition of existing in this part of the universe at this point in its history. The word fall is worth staying with a little longer, because it is doing something specific here, and it would be easy to slide past it. In everyday experience, falling implies a downward direction, implies acceleration, implies an end point, the ground, the impact, the stop. But in physics, falling has a more general meaning, motion under gravity, without a propulsive force countering it. An orbit is a kind of falling. The moon is falling toward the Earth, continuously and continuously missing it, the sideways motion carrying it past the point of impact so that the fall becomes a circle, or close enough to one. The galaxy's motion toward the Great Attractor is falling in this broader sense. Not straight-line collapse toward a point, but motion shaped by gravity, curved by the distribution of mass across a vast region of space, complicated by the expansion of space itself, resulting in a trajectory that is, this is the honest version, not fully resolved, not perfectly understood. The models are good, the measurements are real, the motion is established. But the precise future of that motion, whether the local group will ever approach the attractor's center, whether the expansion will win, what the structure of the attractor actually is at its heart, some of that remains open, and perhaps it should be allowed to remain open rather than forcing a resolution the data doesn't quite support yet. The falling is real. The falling is happening right now. The falling has been happening, this steady wordless motion through space towards something hidden behind dust, for longer than the word for it has existed. There is a certain kind of noticing that becomes available when you stop trying to make something comprehensible and simply allow it to be the size it actually is. The motion is that size. It operates at a scale that has no human analogue, no daily experience that maps onto it, no object you can hold up beside it for comparison that would do anything other than underscore the distance between the human and the cosmic. And still, the motion includes you. The falling includes your body, your weight against the mattress, the warmth of the room around you, all of it carried in the same flow, falling together toward the same unseen point in the southern sky. The dust that hides it will come up again later. What astronomers eventually found when they looked through it, in wavelengths the dust couldn't stop, is a different chapter with a different quality of light. But for now, the falling is enough. The motion is enough. You don't need to see what you're falling toward for the falling to be real. At some point in the mid-1980s, someone had to write it down. Not the phenomenon that had been written down many times, in the careful language of redshift surveys and velocity field analyses, and papers about bulk flows and peculiar motions. But the thing itself, the source of the pull, the object or region or structure that all those peculiar velocities were pointing at, that needed a name, something short enough to use in conversation, specific enough to refer to unambiguously, stable enough to survive being cited across different papers by different groups who might not agree on every detail of what it was, but needed to agree on what to call it. The name that emerged was 2 words and a definite article: the Great Attractor. Names in science are not always neutral. This seems worth establishing early, because it is easy to treat nomenclature as purely administrative, a label attached to a thing for convenience, carrying no content of its own, interchangeable in principle with any other label that would serve the same indexing function. But names are not interchangeable in practice. They arrive with weight, they arrive with implication, and once they are in circulation, once they have appeared in enough papers and been repeated in enough conference talks, they begin to shape the way the thing they name is thought about, not just referred to. The Great Attractor is a name that implies a single object, a thing, a discrete source with a location and a boundary, something you could, in principle, point at and say, there, that is what is pulling us. But what the evidence actually showed, what the data from the 1980s and 1990s accumulated toward across multiple surveys and analyses, was something less definite: a region, a concentration of mass distributed across a large volume of space, involving multiple galaxy clusters, significant amounts of dark matter, structural filaments connecting over denser regions in ways that made the idea of a single central object increasingly difficult to defend. The name had already stuck by the time this complexity became clear. There is a specific location that gets called the center of the Great Attractor, a point in the constellation Norma in the southern sky, at roughly the right ascension and declination that various independent analyses converge on as the approximate gravitational focus of the flow. Near this point sits a galaxy cluster called Abell 3627, one of the most massive clusters in the nearby universe, discovered to be as massive as it is largely because it was hidden behind the zone of avoidance until infrared and radio surveys began to penetrate the dust. Abell 3627 is sometimes described as the Great Attractor. This is convenient and not entirely wrong, and also not entirely right. It is the largest single identified structure near the center of the pull, but the pull is not sourced entirely in Abell 3627. The mass contributing to the flow is distributed more broadly across the Norma cluster, across surrounding salmons and walls of galaxies, across a region sometimes called the Great Attractor region to distinguish it from any single object within it. The name points at a region and implies an object. The region is real. The object, as a discrete thing with edges, is somewhat invented, a useful fiction maybe, or at least a useful simplification that science eventually outgrew while the name remained. There is something that almost resolves here into a clean parallel. The way a name can be a kind of gravity itself, pulling subsequent thinking into orbit around it, shaping the questions that get asked. But that comparison starts to do more decorative work than clarifying work, so it's better left where it is. What is simpler and more useful is this: the name Great Attractor organized a research program. It gave disparate groups working on peculiar velocities and large-scale structure a shared reference point, a common noun around which disagreements could be structured. You can disagree productively about what the Great Attractor is if you both accept the term. You cannot have the same disagreement if one person is calling it the Norma over density, and another is calling it the Centaurus concentration, and a third hasn't assigned it a name at all. In this way, the name did real scientific work independent of whether it accurately described what it named. It enabled coordination. It enabled argument. It enabled the accumulation of results that would eventually complicate the picture the name implied. The 7 Samurai, the informal name given to the group of 7 astronomers whose 1987 paper used the term Great Attractor in print and helped establish it, were themselves aware that they were naming something they didn't fully understand, This is not unusual in science. Newton named gravity before anyone understood what it was. The word electron existed before the particle it named was characterized. Naming often precedes understanding. The name is a placeholder that marks a place in the map where something real is believed to exist, even when the nature of that thing is not yet settled. What followed the 1987 paper was not consensus, but productive disagreement. Other groups questioning the mass estimate, questioning the location, questioning whether the flow was as coherent as the paper suggested. Some argued the attractor was less massive than claimed. Some argued the flow extended further and implicated additional structures beyond the attractor itself, structures further away, larger, that the original analysis hadn't accounted for. The disagreements were, in retrospect, mostly right. The original estimates were too simple. The picture was more complicated than a single attractor could accommodate. The name turned out to describe not a final answer, but an early approximation of something real and large, and still not entirely resolved. It seems worth noticing that this is a common trajectory in cosmology, and in science more broadly, though cosmology has a particular talent for it. An observation that doesn't fit the model, a name attached to the anomaly, a research program organized around the name surviving into a period when the understanding has moved well past what the name originally implied. The name lingering because it is too embedded to replace, too useful to discard, even when it is not quite accurate. The Great Attractor is still called the Great Attractor. It appears in papers published last year. It will probably continue to appear in papers published next year. It names a real phenomenon. It implies a simpler object than the phenomenon turns out to be. Both of those things are simultaneously true, which is perhaps a minor contradiction, or perhaps just an ordinary feature of how language works when it is applied to physics that is genuinely complicated. It seems reasonable to hold both at once. What the name did not do, could not do, was close the question it named. The Great Attractor is still not fully mapped. The mass estimates have been revised upward significantly from the original figures, partly because infrared surveys revealed structures in the zone of avoidance that the original analysis couldn't access, and partly because the picture grew to include structures beyond the attractor itself, further away, more massive in aggregate, contributing their own pull to the flow. The name was attached to a piece of the answer. The answer kept growing. What it grew into, a supercluster, a revised map of the entire cosmic neighborhood, a new understanding of where our galaxy actually lives, is a later chapter. The name comes first. The names always come before the understanding catches up, and the understanding never quite finishes catching up, and the name remains. 2 words and a definite article, still attached to something still being figured out. The first thing to understand about infrared light is that it's not exotic. It is not a specialized scientific tool invented to solve a particular problem. It is simply light, electromagnetic radiation, at wavelengths slightly longer than what human eyes can detect, sitting just past the red end of the visible spectrum the way ultraviolet sits just past the violet end. The eye didn't evolve to see it. That's the only reason it feels like something special rather than something ordinary. Heat produces it. Everything warm produces it. Your body produces it right now, radiating infrared into the room around you, which is why thermal cameras can find people in darkness. Stars produce it. Galaxies produce it in enormous quantities, from their stars, from their warm gas, from the dust within them that absorbs starlight and re-emits it at longer wavelengths. And crucially, the dust of the galactic plane, the same dust that extinguishes visible light so effectively, is largely transparent to the longer infrared wavelengths. Not perfectly transparent, not transparent to all infrared equally. but transparent enough that a telescope sensitive to the right infrared bands can see through regions of the sky that are completely opaque to an optical instrument. This is what changed the picture. For most of the 20th century, sky surveys were optical surveys. Photographic plates sensitive to visible light, cataloguing galaxies across the sky wherever they could be seen, which meant, effectively, everywhere except the zone of avoidance. The gap in those catalogues was accepted as an instrumental limitation, a feature of the observation rather than a property of the universe, and cosmologists working on large-scale structure learned to work around it, to model what might plausibly lie behind the obscured region based on what was visible on either side. The models were reasonable. They were also, it turned out, incomplete. In the 1980s and 1990s, infrared sky surveys began systematically covering regions that optical surveys had left blank. The IRAS satellite, the Infrared Astronomical Satellite launched in 1983, produced the first all-sky survey in the infrared, and while its resolution was limited, it revealed galaxies in directions where optical surveys had found nothing. Later surveys improved on this. The 2MAS-S survey, the 2-micron all-sky survey, catalogued hundreds of millions of objects across the whole sky in near-infrared wavelengths, penetrating the zone of avoidance well enough to reveal galaxy distributions that had been invisible to earlier instruments. What they found in the direction of the Great Attractor was more mass than the optical surveys had suggested, not a little more, significantly more. Abell 3627 is a galaxy cluster. That much was known before the infrared surveys. It appeared in the Abell catalogue of rich galaxy clusters, compiled in the 1950s from photographic plates. But its position near the galactic plane meant that its full extent was obscured, its distance uncertain, its mass poorly constrained. It was catalogued as an object without being well understood as one. When near-infrared observations began to penetrate the dust more effectively, the cluster resolved into something considerably larger than earlier estimates had implied. The density of galaxies around it, the mass concentration, the velocity dispersions of member galaxies, all of these pointed toward a cluster massive enough to contribute substantially to the gravitational pull that the peculiar velocity surveys had been measuring. Is this the Great Attractor? Is that really what's happening? A single cluster massive enough to account for the entire flow? The answer, developed slowly across multiple analyses and surveys, was partly. Abell 3627 is a major component of the gravitational overdensity at the approximate center of the attractor region. It is probably the dominant single structure near that center, but the flow that the peculiar velocity surveys measured extends over a region so large that no single cluster, however massive, could fully source it. The mass had to be distributed in clusters surrounding Abell 3627 in the filaments connecting them, in the larger structural context of which the Norma cluster is just the densest part. The infrared surveys made this complexity visible in a way that optical surveys had not been able to. To an already well-mapped region, another to an already well-mapped region, another point on a curve that was already taking shape. Data that fills a gap arrives with a different charge. It doesn't just extend the picture, it revises it. The thing you were modelling in the blank space turns out to be different from the model. Not always dramatically different, not always wrong in the ways you might expect, but different enough that the picture has to be redrawn rather than just extended. The infrared surveys filled a gap. What they found revised the picture of the Great Attractor region from a zone of inferred mass to a zone of measured mass. Not perfectly measured, not completely mapped even now, but measured well enough to show that the visible universe on the other side of the dust was structured differently from what optical surveys had been able to suggest. There were rivers of galaxies where the map had been blank, clusters, walls, the kind of large-scale structure, sheets and filaments and voids that cosmologists had been mapping in the visible parts of the sky, now appearing in a region that had been a systematic absence for decades. The process of reading infrared data is not immediate. A signal arrives at a detector, not a photographic plate but a semiconductor array sensitive to longer wavelengths, and the signal has to be calibrated, cleaned of instrumental artifacts, corrected for the emission of the telescope itself, which also radiates in the infrared and must be carefully subtracted from the data. The result is a map of infrared brightness across a region of sky, which then has to be interpreted. Which signals are stars within our galaxy, which are distant galaxies, which are artifacts, which are real sources that need to be followed up with other instruments. This process, repeated across the whole sky, across multiple surveys, across years of observation and analysis, produced the revised picture of the Great Attractor region, not in a single discovery moment, not in a paper that overturned everything at once, but in the gradual accumulation of better data filling a better map. The map is still being improved. The zone of avoidance has not been fully penetrated even by the best current infrared surveys. The densest region still present challenges, and there are directions toward the galactic center where even infrared is significantly attenuated. But the picture is incomparably better than it was before the first infrared satellite looked at the sky. What the infrared showed in summary, though summary does some violence to the texture of how the knowledge actually developed, was a region of genuine mass concentration broadly consistent with what the peculiar velocity surveys had inferred, but more complicated in its internal structure than a single attractor object could represent. Multiple clusters, extended filaments, mass distributed across a volume of space large enough that its gravitational influence could reach the distances that the velocity surveys had always implied it must. It seems, in retrospect, that the infrared surveys didn't so much solve the mystery of the Great Attractor as give it a more detailed face. The pull was already established. The infrared data gave the source of the pull a structure, incomplete, still being refined, but real. Galaxies where there had been a blank, clusters where there had been an inference, mass where there had been a model. The blank had always been occupied. The instruments just needed time to find the right kind of light to cross it with. And what the infrared surveys also began to suggest, tentatively at first, then more clearly as additional data came in, was that the Great Attractor region, however massive, might itself be embedded in something larger still, a superstructure further away, contributing its own gravitational pull to the flow. A concentration of mass so remote that even the peculiar velocity surveys of the 1980s hadn't clearly separated its influence from the attractors. That structure, the Shapley Concentration 500 million light-years away, would take longer to characterize. It sits beyond the attractor in the same general direction of the sky, adding its pull to the pull, deepening the flow that the peculiar velocity surveys had first measured, without knowing its full source. The infrared opened a window. What was seen through it suggested there were more windows still to open. The observable universe is approximately 93 billion light-years across. That number is not a distance in the ordinary sense. It is not the distance to a wall or an edge, but the distance to the horizon of what light has had time to reach us from since the universe became transparent to radiation, roughly 400,000 years after the Big Bang, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen and the universe went, in the span of cosmic time from opaque to clear. Everything within that horizon has had time in principle to send light toward us that we could receive today. Most of it is very far away. Within the observable universe there are an estimated 2 trillion galaxies, though that figure has been revised several times and may be revised again as instruments improve and the counts in different regions of sky are reconciled with models of galaxy formation and evolution. 2 trillion is a number that does not compress into anything useful at human scale. The Milky Way contains somewhere between 100 billion and 400 billion stars, depending on how the lower mass end of the stellar population is counted, which is difficult because small dim stars are hard to detect individually across large distances. One galaxy, 100 to 400 billion stars, 2 trillion galaxies. The arithmetic is available but does not produce comprehension. It produces a number larger than the first number, which is itself already beyond what human intuition can hold, and the result is not understanding but something more like the awareness of a distance between the mind and the scale it is trying to approach. That distance is worth acknowledging rather than papering over with a reassuring analogy. The Great Attractor sits at a distance of roughly 200 to 250 million light-years from Earth. This figure has been revised since the first estimates of the 1980s, which placed it closer, around 150 million light-years, before better data and more sophisticated analyses pushed the estimate outward somewhat, as better data in cosmology tends to do, 250 million light-years. Within the observable universe, this is not an extreme distance. It is well within the range of what current telescopes can study in considerable detail. Spectroscopy, imaging, velocity measurements, X-ray observations of hot intracluster gas. The Great Attractor region is not at the edge of what is accessible. It is, in cosmic terms, in the neighborhood. And yet, 250 million light-years means that the light arriving now from the galaxies in the Norma cluster, the cluster that sits closest to the gravitational center of the attractor, left those galaxies 250 million years ago. At that time on Earth, the Permian period was approaching its end. The Permian-Triassic extinction event, the largest mass extinction in the history of life on this planet, the event that eliminated somewhere between 90 and 96% of all marine species and 70% of terrestrial vertebrate species, had not yet occurred. Dinosaurs had not yet evolved. The light that carries current information about the Norma cluster to a telescope operating today was already travelling through space before the first dinosaur existed, and it continued travelling through the entire span of the Mesozoic era, through the extinction of the non-avian dinosaurs, through the entire Cenozoic, through the evolution of every primate lineage, through the emergence of the genus Homo, through the entirety of human history, and arrives continuously at detectors that have existed for a few decades at most. This is the actual relationship between the observation and the thing observed, not a metaphor for distance. The distance itself expressed in events that happened on a planet the light has never touched, events that unfolded in the time it took the light to cross the space between the source and the receiver. What a telescope sees when it looks at the Norma cluster is not the Norma cluster as it exists now. It is the Norma cluster as it existed when the light left, a snapshot from the Permian, in the rough sense that the Permian is when the exposure began. The Norma cluster as it exists at this moment, in whatever configuration 250 million more years of gravitational evolution have produced, is not visible to any current instrument and will not be visible to any instrument for 250 million more years, by which point the Sun will be considerably older and the Earth may or may not still be habitable in any form recognizable to current life. These are not comfortable thoughts to linger on necessarily, and perhaps that is the wrong frame for them. Comfort or discomfort are not particularly useful categories here. and it seems better to simply let the facts be what they are without adding a layer of feeling about them on top. The distance is 250 million light-years. The light is old. The cluster is massive, among the most massive in the local universe, with a total mass estimated in the range of 1 quadrillion solar masses when dark matter is included, though estimates of this kind carry significant uncertainty. And perhaps that hesitation belongs here, the acknowledgement that the number is a best current estimate rather than a settled value. The pull the cluster exerts, along with the distributed mass of the broader attractor region, the surrounding clusters and filaments and overdensities, reaches across that distance and leaves a measurable imprint on the velocities of galaxies much closer to us, including our own. The physics of how gravity propagates across these distances is general relativity, the curvature of space-time by mass, the way that curvature influences the trajectories of everything moving through it, including galaxies moving under their own peculiar velocities through an expanding universe. The mathematics of this is settled. The result, a coherent flow of galaxies toward the attractor, is measured. 100 million light-years was the early estimate for the distance. 250 million is the current estimate. The difference between those numbers is itself larger than the distance from Earth to the Virgo cluster, the nearest large galaxy cluster to our local group, the cluster that sits at the center of the Virgo supercluster, the structure that cosmologists used to consider our home supercluster before the map was redrawn. The revision in the distance estimate did not change the physics. The pull was the same pull before and after the revision. The galaxies were moving at the same velocities. The mass was where it was regardless of what the estimates said. The estimates caught up to the mass, gradually, across years of improving data and analysis, in the way that estimates in cosmology tend to, not by sudden revision, but by the slow pressure of better instruments and larger surveys and more sophisticated models applied to the same underlying reality. 250 million light-years. The number sits at the center of this chapter, and has, in a sense, been the chapter's only real subject, not the object at that distance, not the physics of how it was measured, but the distance itself, approached from different angles, expressed in different terms, allowed to be what it is without being made more manageable than it actually is. It is not manageable, it is real. The light crossing it right now, carrying information about the attractor region toward instruments that don't yet exist, began its journey before anything alive on Earth today had any ancestor capable of looking at a sky and wondering what was in it. That light is in transit. It has been in transit longer than life on Earth has had eyes. It will arrive. In 2014, the map changed. Not the universe. The universe didn't change. It never does in response to being looked at, never rearranges itself to match a new description. What changed was the description. A paper published in the journal Nature by a team led by astronomer Brent Tully redrew the boundary of the structure we live inside, and in doing so gave it a name, Laniakea. The word is Hawaiian. It means, roughly, immeasurable heaven. To understand what the paper did, it helps to understand what a supercluster is, or rather, what it had been understood to be before 2014, because the definition shifted somewhat with this work. The traditional picture of a supercluster was a region of space containing an above-average density of galaxies and galaxy clusters, defined by the spatial distribution of those galaxies, where they are essentially rather than how they are moving. On this definition, our local group belonged to the Virgo supercluster, a structure centered on the Virgo cluster, the nearest large galaxy cluster to our neighborhood, roughly 50 million light-years away. The Virgo supercluster is real. It is dense. It is a genuine overdensity in the distribution of matter in this part of the universe. But Tully's team used a different definition. Instead of asking where galaxies are, they asked where galaxies are going, mapping the peculiar velocity field across an enormous region of space, tracing the flow lines, following them to see where they converged. What they found was that the flow lines, the paths of galaxies moving under gravity, independent of the overall expansion of space, converged toward a single basin of attraction, a region toward which everything within an enormous volume was, in the language of the analysis, falling. That basin of attraction, that convergence point, was the Great Attractor region. The structure defined by the flow field, everything whose peculiar velocity was directed ultimately toward the same gravitational center, turned out to be vastly larger than the Virgo supercluster. It contained the Virgo supercluster entirely. It contained our local group. It contained the Centaurus cluster, the Hydra cluster, the Antlia cluster, the Great Attractor region itself, and hundreds of thousands of other galaxies distributed voluminous space spanning roughly 500 million light-years. 500 million light-years, containing approximately 100,000 galaxies, with a total mass somewhere in the range of 100 million billion solar masses. This is Laniakea. This is where we live. The name carries something, not because of what it means in translation. Immeasurable heaven is beautiful, but it is also a phrase, a combination of sounds attached to a concept, and the concept is what matters, but because of what it does to the picture. Before Laniakea, our cosmic address was the Milky Way, the local group, the Virgo supercluster, a hierarchy of structures, each containing the last, each progressively larger. After Laniakea, the hierarchy extended one more level, and the level it extended to was defined not by where mass sits, but by where it is going. The supercluster is not a clump. It is a watershed, a basin. Everything in it is, in the technical sense, in the same gravitational catchment area, draining toward the same low point the way rivers in a watershed drain toward the same sea. The Great Attractor is that low point, or near it. The actual gravitational minimum of Laniakea is in the attractor region, approximately where Abel 3627 and the surrounding mass concentration sit, the dense heart of the structure toward which 100,000 galaxies are collectively falling, including this one. There is something that takes a while to settle about being inside a structure you didn't know existed, not the Great Attractor that had been named and studied for decades by 2014, but Laniakea as a whole, as a single coherent structure with a boundary and a name. Before the paper, the Milky Way was in the Virgo supercluster, a structure that felt large but also felt like a cluster of clusters, a distribution of mass in a region, not a dynamic system with a shape defined by motion. After the paper, the Milky Way was near the edge of Laniakea, not at the centre, not at the heart, but out toward the periphery in the region of the local group, which sits on the outskirts of the structure rather than near its gravitational core. We are not at the centre of what we belong to. We are, and this is the measured result, not a metaphor, near the edge of our supercluster in a relatively quiet part of the structure, far from the attractor that defines its boundary. That boundary, by the way, is not a wall. It is a divide. The line where the flow field changes direction, where peculiar velocities shift from pointing inward toward Laniakea to pointing outward toward the next basin of attraction. Cross it in the right direction, and your galaxy, given enough time and ignoring the expansion of space, would eventually fall not toward the Great Attractor, but toward some other gravitational center entirely. The boundary is real. It is defined by the physics. It has no fence. The Milky Way sits inside Laniakea. That is a sentence that was not true, not known to be true, before 2014. It became true in the sense that any scientific statement becomes true through evidence, through analysis, through the application of a method rigorous enough to produce a result that other researchers could check and largely accept. It is worth pausing here, just briefly, because it seems like the kind of thing that should feel more significant from the inside than it perhaps does. Humanity learned within living memory that it lives inside a supercluster spanning 500 million light-years, with 100,000 galaxies falling toward a gravitational center 250 million light-years away. That is a recent piece of knowledge, not ancient, not established for generations, recent. And the learning of it changed nothing about the motion. The falling was already underway. The structure was already what it was. The flow field was already shaped exactly as the analysis described. The name Laniakea landed on a thing that had existed for billions of years, unnamed, uncharacterized at this scale, simply there, the watershed it had always been, the 100,000 galaxies already in it moving the way they had always moved, the Great Attractor region already sitting at its gravitational heart. There is a hesitation that comes when trying to say something true about what it means to belong to a structure this large, the sense that any phrasing will either overstate it or understate it, that the scale resists the kind of sentence that might make it feel immediate. Maybe that resistance is the honest response. Laniakea is 500 million light-years across. The Milky Way is 100,000 light-years across. The ratio between them is 5,000 to 1. A cell in your body relative to the length of a football field is closer in ratio than the Milky Way is to Laniakea. And yet the Milky Way is a member, a participant in the flow. One of 100,000 galaxies whose peculiar velocities, when mapped and traced, define the boundary and the shape of this structure. Membership here requires nothing. It cannot be resigned from. It was not chosen and cannot be changed. It is simply the gravitational condition of existing where we exist, at this point in the history of the universe. In 2014, astronomers gave a name to the place we live. And the place had been there, exactly as described, for longer than the Earth had been a planet. The name arrived late, as names tend to. The structure didn't wait for it. The 100,000 galaxies didn't pause their falling. The Great Attractor didn't hold its mass in reserve until someone decided what to call the region it anchors. The map changed. The territory had always been this shape. You live inside it now, as you have always lived inside it, as everyone who has ever existed on this planet has always lived inside it, in a quiet corner of an immeasurable heaven, near the edge of a structure defined by where everything in it is slowly going. The falling has always been the definition. The name just made it easier to say. Behind the Great Attractor, there is more. This is not a dramatic statement. It is simply what the data showed, gradually, as the surveys improved and the velocity fields were mapped across larger and larger volumes of space. The Great Attractor was real. The flow toward it was real, and the flow, when traced carefully, didn't quite stop at the attractor. It continued in the same general direction, as if the attractor were a significant feature in a landscape that had deeper slopes still further out. Something else was contributing. The Shapley supercluster, sometimes called the Shapley Concentration, after the American astronomer Harlow Shapley, who noted the unusual density of nebulae in that region of sky in the 1930s, sits at a distance of approximately 500 million light-years, roughly twice as far as the Great Attractor. Shapley noticed the concentration long before redshift surveys existed, long before the concept of a supercluster had been formalized, long before anyone had the tools to measure what the concentration actually was in terms of mass or the distance. He noted it as an over-density on photographic plates, a region where the count of faint nebulae, what we now know to be galaxies, was unusually high. The observation sat in the literature. It was not ignored exactly. It was pending in the way that many observations spend years pending before the right question arrives to make them relevant. The right question arrived when cosmologists began working out why the peculiar velocities of galaxies in our neighbourhood were as large as they were, and found that the Great Attractor alone, even at the revised mass estimates the infrared surveys had produced, didn't quite account for all of it. The Shapley Concentration is, by most measures, the most massive structure in the observable universe within 1 billion light-years of Earth. That sentence deserves a moment. Not because it is alarming, it isn't in any practical sense, but because it reframes the gravitational landscape of our cosmic neighbourhood in a way that the Great Attractor alone doesn't capture. The attractor is a significant concentration. Shapley is larger, much larger, a region containing dozens of galaxy clusters, multiple rich cluster cores, an estimated total mass somewhere in the range of 10,000 times the mass of the Milky Way. No, that comparison doesn't work at this scale. The ratios become meaningless. More usefully, a region whose total mass, when dark matter is included, exceeds that of the Great Attractor region by a substantial factor, and it sits, from our vantage point, in roughly the same direction of sky. Behind the attractor, further out, adding its gravitational pull to the pull that the attractor was already exerting. The degree to which Shapley contributes to the peculiar velocity of our local group, to the bulk flow that carries the Milky Way and its neighbours through space, has been debated across multiple generations of surveys and analyses. Early work suggested the contribution was significant but secondary, the Great Attractor dominant, Shapley a supplementary influence at the edge of the relevant volume. Later work, using better velocity field maps and more complete galaxy catalogues, suggested the Shapley contribution was larger than early estimates had allowed. Some analyses placed it at roughly equal importance to the Great Attractor for the total observed bulk flow. Others maintained the hierarchy, with the attractor dominant and Shapley contributing but subordinate. The honest position is that the decomposition, how much of the flow belongs to which source, is not fully settled. The flow itself is measured. Its sources, separated and attributed, remain a subject of active refinement. This is not a failure of the science. It is what the science actually looks like when the object being studied is a velocity field spanning hundreds of millions of light-years, sourced by mass distributions that are themselves only partially mapped. The measurement is easier than the attribution. The attribution requires modelling, and models carry assumptions, and different reasonable assumptions produce somewhat different decompositions. There is something worth sitting with here. The idea that our motion through space has more than one cause, that the flow we belong to is the product of multiple gravitational influences operating at different distances, each contributing its share to the net velocity, none of them individually sufficient to explain the whole. The universe doesn't simplify for measurement. It has as many causes as it has, and the work of separating them is the work of decades of surveys and the work of still more decades to come. 500 million light-years. The light arriving now from the Shapley concentration left its source galaxies 500 million years ago. On Earth, at that time, the Cambrian explosion had already occurred. The extraordinary proliferation of complex animal body plans that transformed the biosphere of the planet, and the long Paleozoic era was underway, filling the seas with organisms whose descendants would eventually develop limbs and lungs and the capacity to build instruments sensitive enough to detect the light now arriving from a supercluster 500 million light-years away. The light was already in transit before fish had fully colonized the oceans. It crosses space that is, for the most part, empty in the sense that cosmological space is empty, not truly void, threaded with the cosmic web of filaments and sheets and the faint warm gas of the intergalactic medium, but empty enough that a photon can travel for 500 million years and arrive essentially unchanged, carrying the spectral signature of the galaxy that emitted it, readable by an instrument that will exist for perhaps a few more decades before being replaced by something better. The Shapley concentration is visible. Unlike the Great Attractor region, it does not sit behind the zone of avoidance. It lies in a part of the sky where the galactic dust column is thin enough for optical surveys to reach it. This means it has been mapped more completely than the attractor, its galaxy clusters catalogued, its mass estimated from multiple independent methods. The visibility didn't lead to immediate understanding of its role in the local velocity field. That required the velocity surveys, the measurement of peculiar motions across the intervening hundreds of millions of light years, and the modelling to connect the observed motions to the sources responsible for them. Seeing a structure and understanding its gravitational reach are different problems. Shapley was seen in the limited sense by Harlow Shapley in the 1930s. Its gravitational influence on our motion was not characterized until decades later. The eye gets there first. The understanding follows slowly, when the right measurements become possible. What the Shapley concentration adds to the picture is depth. The Great Attractor is the nearest major gravitational feature in the direction our galaxy is moving. Shapley is further in the same direction, larger in aggregate mass, contributing a pull that stretches across a distance twice as large. Beyond Shapley, the large-scale structure continues. Other superclusters, other concentrations, the cosmic web extending in all directions to the limits of the observable universe. But Shapley is the most significant known structure in this particular direction within the volume where its influence on our local motion is measurable. The flow we belong to is not sourced by a single object. It is the response of our galaxy and our supercluster to a gravitational landscape shaped by at least two major concentrations operating at different distances in the same general direction, plus the distributed mass of the cosmic web surrounding them. This is the actual picture as best as current data can construct it. It is more complicated than a single attractor pulling a single flow. It is also, in a way that takes a moment to recognize, more coherent. The idea that our motion is the cumulative response to everything massive in our gravitational neighborhood, near and far, each contributing according to its mass and its distance, the whole producing the net velocity we carry through space. There is a question that this chapter has been moving toward without quite arriving at, whether the full source of the bulk flow our galaxy participates in is now understood, whether the combination of the Great Attractor and the Shapley concentration accounts for everything in the measured velocity. The answer is probably not entirely, and that is the honest version. Large-scale structure surveys continue to find mass in regions not fully accounted for in earlier models. The velocity field at scales beyond 500 million light-years has contributions that are still being characterized. The picture is better than it was a decade ago. It will be better still in a decade more. The flow is real. Its sources are large. Their full accounting is ongoing. That incompleteness is not a problem to be resolved before sleep. It is simply the condition of the science, accurate in its major features, still improving in its details, pointing at a universe that has more in it than any single generation of instruments has been able to fully see. The next layer inward, what all of this means for gravity at the scale of superclusters, for the physics of how mass this large curves the space around it, is where the chapter after this one goes. The Milky Way is moving towards the Great Attractor. That's been established across several chapters now, built up from peculiar velocity surveys and infrared observations and the remapping of our supercluster. And it is as well supported a fact as cosmology currently offers about our galaxy's motion through space. Not a provisional finding, not a tentative inference, but a measured result that multiple independent lines of evidence converge on. And yet we are not arriving. We have not arrived. We will not arrive in any time frame that the word arrival can meaningfully accommodate. The motion is real and the destination is real, and the distance between them is, for reasons that take a little time to unfold, not closing in the way that ordinary motion toward an ordinary destination closes distance. The reason is the universe itself. Space is expanding. This is the foundational fact of modern cosmology, established first through Hubble's observations of galaxy redshifts in the late 1920s and confirmed and refined through nearly a century of subsequent observation, now understood in enough detail that the rate of expansion, the Hubble constant, though constant is a somewhat misleading word for a value that changes over cosmic time, is measured to a precision that generates genuine scientific controversy because different methods of measuring it produce slightly different answers, and the discrepancy between those answers is itself an active area of research. But the expansion itself is not in question. Space is expanding. The distance between objects not bound to each other by gravity is increasing, not because those objects are moving through space away from each other, but because the space between them is being produced. New space emerging between existing positions, stretching the separations, carrying unbound objects apart in a way that is distinct from ordinary motion through a static background. Feel the difference between those two things for a moment, because it matters physically, and not just semantically. An object moving through space carries momentum. It has a velocity relative to the space it is in, and that velocity has consequences. It produces a Doppler shift in the light the object emits. It can be redirected by gravity. It costs something in the sense that a force is required to change it. The peculiar velocity of our galaxy, 600 kilometers per second toward the attractor, is motion in this sense. Real motion through space with the direction and a magnitude, responsive to gravity, imprinted on the light we emit in ways that other observers can measure. The expansion of space is different. It is not motion through space. It is the growth of space itself, and the recession of distant objects that results from it is not a velocity in the same sense. It does not produce the same Doppler effect. It is not bounded by the speed of light in the same way. It cannot be redirected by applying a force to the receding object because there is no motion to redirect. The two things coexist. Our galaxy has a peculiar velocity toward the attractor, a real motion through space, directed and measurable, and simultaneously the space between our galaxy and the attractor is expanding, the distance stretching at a rate proportional to the distance itself. The larger the separation, the faster the expansion adds to it. At 250 million light-years, the expansion is adding distance at a rate that, in the current epoch, competes meaningfully with the peculiar velocity trying to close it. Whether our galaxy will ever genuinely approach the center of the Great Attractor, reduce the distance rather than merely slow its growth, depends on the balance between the gravitational pull toward the attractor and the expansionary push of space itself. And that balance is, it is tempting to say this resolves cleanly, that the numbers give a definitive answer, but the honest version is more careful than that. The balance is sensitive to assumptions about the total mass of the attractor region, the distribution of that mass, the precise value of the cosmological constant governing the expansion, and the trajectory of the expansion rate over cosmic time. The current consensus, to the extent there is one, leans toward a picture in which the local group is gravitationally bound within Laniakea to some degree, meaning the expansion has not yet won entirely at these scales. But the long-term fate of that binding under an accelerating expansion is genuinely uncertain in the details, and any claim of certainty here would be overstating what the models actually deliver. The expansion is accelerating. This is the other foundational fact, established in 1998 through observations of Type 1a supernovae, a type of stellar explosion that occurs at a consistent intrinsic brightness, making it usable as a distance marker across vast stretches of the universe. The supernovae were fainter than expected, which meant they were further away than expected, which meant the universe was expanding faster at large distances than a decelerating expansion would produce. The expansion was speeding up. The cause assigned to this acceleration is called dark energy, a name for something whose nature is not understood, whose presence is inferred from its effect on the expansion rate, which is real and measured and uncontested, even though the underlying physics that produces it remains one of the deepest open questions in physics. Dark energy acts in its effect on cosmological expansion like a property of space itself, an energy density inherent to the vacuum present everywhere, constant in magnitude and in its influence on the expansion rate, dominant over gravity at large scales. At small enough scales, within galaxies, within galaxy clusters, within gravitationally bound systems like Laniakea, gravity wins locally. The expansion is overcome. Objects remain bound, orbit each other, fall toward common centers of mass. At large enough scales, between superclusters, across the void separating the great structures of the cosmic web, dark energy wins. The expansion carries structures apart faster than gravity can draw them back. The Great Attractor sits at a scale where these two influences are not trivially resolved. The attractor is massive, the distance is large, the expansion is accelerating, the local gravitational binding is real. Which influence dominates over what time scale, for which parts of the structure? This is the physics of the situation, and the physics does not currently offer a single clean answer that applies uniformly across the entire attractor region and the full span of Laniakea. There is something worth sitting with in this, not as a source of unease, but as a genuine feature of the situation, which is that the motion we participate in, the falling that has been running for billions of years and continues tonight as you lie still and the galaxy moves, may be motion that never concludes. Not because it stops, not because the attractor weakens or the velocity reverses, but because the destination itself is being carried by the same expansion that the motion is working against, the gap opening as the motion tries to close it, the distance between the mover and the move towards stretching in the same time that the mover crosses it. A river that runs toward a sea while the sea moves away at a rate comparable to the river's flow will run indefinitely and arrive at nothing. And yet the running is real, the motion is real, the water is genuinely moving in the direction of something genuine, and none of that is diminished by the incompleteness of the arrival. This seems like an honest description of our situation. The motion is real. It has been real for the entire history of our galaxy, for longer than the solar system has existed, and it continues right now, 600 kilometers every second in the direction of Centaurus, toward a gravitational center that the expansion of space is simultaneously carrying further away. The falling does not require an arrival to be real. The physics is not incomplete because the destination recedes. The physics is exactly what it is. Gravity and expansion in competition across a scale where neither one trivially wins, producing a motion that is genuine and measurable and indefinitely ongoing. The universe is large enough to contain motion that never concludes and still means exactly what it appears to mean. The next chapter asks what all of this gravity actually is at this scale, not the familiar gravity of planets and orbits, but something operating across hundreds of millions of light years, written into the geometry of space itself, shaping the trajectories of structures that contain hundreds of thousands of galaxies. It is a slower chapter than this one. There is a version of science communication that saves the uncertainties for last, tucking them into a final paragraph after everything solid has been established, the way a careful writer might place a qualification at the end of a sentence rather than the beginning, acknowledging the limit without letting it dominate. And there is something understandable in that approach, the desire to give the knowledge its full weight before introducing what the knowledge hasn't yet reached. But the uncertainties in this particular subject are not small, and they are not peripheral, and placing them at the end would give a false impression of how much of the picture is actually settled versus how much is still being worked out, which is why this chapter arrives here, not at the end, while the subject still has significant territory ahead of it. The total mass of the Great Attractor region is not known with precision. This is not a temporary gap waiting for one more survey to close it. It is a genuinely difficult measurement problem that has occupied researchers for decades and continues to produce a range of estimates rather than a settled value, because the mass is distributed across a large volume in forms that are not all equally accessible to current instruments, because the zone of avoidance still obscures parts of the relevant sky, even in the infrared, and because the dark matter component, which constitutes the majority of the mass in any large gravitational structure, cannot be observed directly and must be inferred from its gravitational effects, which themselves depend on assumptions about the distribution and dynamics of the visible matter used to trace it. The estimates that exist are real estimates, grounded in real data, produced by careful analysis using the best available methods. They span a range. The lower end places the attractor region at a mass comparable to a large galaxy cluster, enormous by any ordinary standard, but at the lower boundary of what would be needed to produce the observed flow. The higher estimates, which incorporate more of the surrounding structure and account more fully for the contribution of dark matter, are substantially larger, by factors of several in some analyses, which is not a small difference when the object being measured is already among the most massive structures in the local universe. The peculiar velocity field, the map of how galaxies are moving relative to the overall expansion, which is the primary observational evidence for the attractor and its mass, is itself a measurement that carries uncertainty, propagating through from the distance measurements on which it depends. Peculiar velocities are calculated by comparing a galaxy's observed recession velocity to the recession velocity predicted by its distance, and the distance has to be measured independently, using methods, the Tully-Fisher relation, the fundamental plane, Type I supernovae, Cepheid variable stars, each of which carries its own calibration uncertainties, its own scatter, its own systematic errors that do not always cancel when results from different methods are combined. The flow is coherent enough that its reality is not in question. Too many independent surveys using too many independent methods have found the same bulk motion for there to be serious doubt about whether the flow exists. But the precise amplitude of that flow, which directly determines the mass estimate for the source, is sensitive to these distance measurement uncertainties in ways that are difficult to fully eliminate. Better surveys reduce the scatter. They do not eliminate it. Beyond the attractor, the picture becomes more complicated still, and perhaps this is where the genuine uncertainty of the subject becomes most apparent. Not in the attractor itself, which is at least well localized and well studied, but in the question of how the local flow, relates to the larger scale velocity field extending out to the Shapley concentration and beyond. The Shapley concentration contributes to the bulk flow, as the previous chapter discussed, but the precise magnitude of that contribution depends on the same distance measurement uncertainties that affect the attractor analysis, compounded by the greater distance involved, 500 million light-years, where the measurement methods are stretched toward the edges of their reliable range. And beyond Shapley, the large-scale structure continues in ways that current velocity surveys have not fully characterized. There may be contributions to the local flow from structures at even greater distances, over densities in the cosmic web at scales that current surveys are only beginning to map. The flow is embedded in a gravitational landscape that extends further than the best current measurements reach, and the part that lies beyond the current reach contributes something to the motion, the exact amount still being worked out. There is a particular kind of intellectual honesty that is harder to practice than it sounds, the kind that doesn't reach for a resolution when the data doesn't yet support one, that holds an open question openly rather than closing it prematurely with a best current guess stated as a finding. And it seems worth saying that the science around the Great Attractor has not always achieved this perfectly, that early papers sometimes stated mass estimates with more confidence than the underlying data warranted, that the history of this subject includes revisions that were large enough to matter, and that required subsequent papers to walk back claims that had been stated too firmly. This is not a criticism of the scientists involved. The history of the subject is actually a fairly ordinary example of how science in a data-limited regime progresses, with early estimates based on limited data being revised as better data arrives. The process working as intended even when individual steps in it overstated their certainty. It is worth knowing, though, when you encounter a precise-sounding number in a science article about the Great Attractor, a specific mass, a specific distance, a specific velocity, that number is a current best estimate from a specific analysis using specific assumptions, and the range of defensible estimates around it is probably wider than the precision of the number implies. What is not uncertain is worth naming clearly. The bulk flow is real, the coherent motion of our galaxy, and thousands of others toward the same region of sky, measured independently by multiple surveys across 4 decades. The attractor region is genuinely massive. Whatever the precise value, the mass concentration in the direction of Norma and Centaurus is among the largest in the local universe, sufficient to produce significant gravitational influence across hundreds of millions of light-years. The zone of avoidance partially obscures the relevant sky. This is a geometric fact about our position inside the galactic disk, not a property of the instruments, and it will continue to complicate observations in the affected directions for as long as we observe from inside the Milky Way. Laniakea is real. The supercluster, defined by the flow field, its boundary determined by where peculiar velocities change direction, is a genuine structure, even if its definition is somewhat different from earlier supercluster definitions, and even if its exact boundary in certain directions is not fully settled. The expansion of space is real. Dark energy is real in its effects, and the long-term fate of the local group's motion relative to the attractor is genuinely uncertain under an accelerating expansion. These are the settled parts. The boundary between what is known and what is still being worked out is not a wall. It is more like a gradient, a region where the confidence fades from high to moderate to low to speculative, and the gradient is wide, wider perhaps than popular accounts of the subject tend to convey, because popular accounts understandably focus on the remarkable parts of what is known rather than the detailed texture of what remains uncertain. The remarkable parts are genuinely remarkable. 100,000 galaxies in a common gravitational basin, a flow spanning 500 million light-years, a gravitational center still only partially mapped, a name attached to something still being figured out 4 decades after the name was first used in print. The uncertainty doesn't diminish any of this. It is part of what the subject actually is, a region of physics and cosmology where the observations are extraordinary, and the instruments are pushing toward their limits, and the models are good enough to be useful and not yet good enough to be final. That condition, accurate in its major features, still improving in its details, is where this chapter leaves the subject. Not because the chapter's run out of things to say, but because that is where the science actually is, and there is no better place to stop than where the knowledge itself stops, at the edge of what the current instruments can reach, with more surveys planned and more data coming and more revisions ahead that will make the picture sharper without ever quite making it complete. The next chapter goes somewhere quieter. Maps have edges, not because the territory does, because maps are made by people, and people work within limits, of instruments, of time, of what the sky will show from a particular place in a particular era. The edge of a map is not a wall in the universe. It is the line where the making stopped. Cosmological maps have moved that line outward, continuously for about a century. In 1920, the known universe was the Milky Way. Not known to be only the Milky Way, there were spiral nebulae scattered across photographic plates, objects whose nature was debated, whose distances were unmeasured, whose relationship to the galaxy was unclear. But the working map, the one used in calculations and models, was essentially galactic. One disk of stars rotating, containing everything that had been measured. Then Hubble measured the distance to Andromeda. The map expanded, not the universe. The map. The universe was the same size it had been. But the picture people were working with changed irreversibly from one galaxy to 2, and then to many, and then to a local group, and then to a local supercluster, and then, in 2014, to Laniakea, 500 million light-years across, containing 100,000 galaxies with the Great Attractor near its gravitational heart. Each expansion of the map took years, decades sometimes. The data accumulated slowly, the analysis took time, the resistance from existing frameworks was real and not always unreasonable. The cosmic web is the current largest scale structure that cosmological surveys have mapped in any detail. It is not a single object. It is a description of the distribution of matter across the observable universe. A network of filaments, the long thin threads of overdense matter, connecting clusters and superclusters, separated by vast voids where matter is sparse and galaxies are few. The whole arrangement looking in projection, something like the structure of a neural network, or a foam, or the interior of a very large sponge. Is that really what's happening? Is it accurate to describe it as a web, with the implications of regularity and pattern that the word carries? Approximately. The large-scale structure has genuine statistical regularity. The power spectrum of density fluctuations follows predictable patterns that come from the physics of the early universe, from the quantum fluctuations that seeded all subsequent structure formation, amplified by gravity over billions of years into the filaments and voids that surveys now map. The web is not a metaphor for something without structure. It is a rough description of structure that is genuinely there. But it is not uniform, not perfectly regular. The filaments vary in density and length. The voids vary in size. The clusters at the intersections vary enormously in mass. The web is a statistical description, a pattern, not a blueprint. The observable universe extends to a radius of about 46 billion light-years in every direction. Within that volume there are an estimated 2 trillion galaxies. Current surveys, the most comprehensive redshift surveys, the maps of galaxy positions and velocities assembled over decades of telescope time, have mapped in meaningful detail a small fraction of that volume. The nearby universe, out to a few billion light-years, with reasonable completeness in the parts not obscured by the galactic plane. The more distant universe, out to the edge of the observable volume in statistical samples, enough to characterize the large-scale structure, to measure the power spectrum, to test cosmological models, but not mapped galaxy by galaxy the way the local volume has been. The Great Attractor sits at 250 million light-years. In the context of the full observable volume, this is nearby, very nearby, a small fraction of the distance to the edge, and it is still not fully mapped. The incompleteness is not uniform. Some directions are better covered than others. The zone of avoidance is the most obvious gap, the band of sky obscured by the galactic plane, where galaxy surveys thin out and eventually fail. But it's not the only incompleteness. Survey boundaries, telescope time limitations, calibration challenges at the faint end of the galaxy, luminosity function, all of these produce a map that is detailed in some regions and sparse in others, comprehensive in some redshift ranges and patchy in others. The maps improve with each generation of surveys. The Sloan Digital Sky Survey mapped hundreds of millions of objects across about a third of the sky, producing the most detailed three-dimensional map of the nearby universe assembled up to its time. The Dark Energy Spectroscopic Instrument operating now is extending that map further in depth and sky coverage, measuring tens of millions of galaxy redshifts to constrain the expansion history and the large-scale structure. Future surveys, the Vera Rubin Observatory, the Euclid Space Telescope, will extend the map again in depth and completeness, adding detail to regions currently sparse. Each new map reveals structure that was inferred but not confirmed, structure that was not expected, structure that requires the models to be adjusted. Adjusting models is not a sign of failure. It is what happens when instruments improve and the universe turns out to be more detailed than the previous instrument could resolve. The Great Attractor was an inference before it was a measurement. The Shapley Concentration was a density on a photographic plate before it was a characterized supercluster. Laniakea was, before 2014, a collection of structures that were known individually but not understood as a single coherent object. The map grew to include each of these. It will grow further. What it will find? There is a genuine answer to that question in the sense that the universe has a structure, and the structure is there whether or not it has been mapped. Future surveys will find whatever is there. Denser regions of the cosmic web then are currently characterized. Voids larger than those currently catalogued. Perhaps structures, superclusters, filaments, concentrations that revise the current picture of our gravitational neighborhood, the way Laniakea revised the picture of our supercluster. Perhaps not. Perhaps the current picture is close to complete at the scales relevant to the local flow, and the refinements ahead are refinements in precision rather than revisions in kind. Both possibilities are real. The data will decide. The edge of the map is not in any fixed place. It moves as instruments improve and surveys extend, and the light that has been travelling for billions of years finally reaches a detector sensitive enough to record it. The edge of the observable universe is fixed, not by the instruments, but by the speed of light and the age of the universe, the horizon beyond which no information can have reached us yet. Between the current edge of the detailed map and the horizon of the observable universe, there is structure. Galaxies, clusters, filaments, voids, the same pattern that appears everywhere the surveys have reached, extending in every direction to the limits of what light can carry. None of it has an outer wall. The observable universe is bounded by a horizon, not a surface. Cross the horizon and you would find more universe, more structure, more galaxies receding into a volume that the expansion is continuously placing beyond reach. The map that cosmologists work with is the best current approximation of a territory that has no edge and no centre. Or rather, every point is equally a centre. Every observer at every location looks out to their own horizon and sees structure in every direction, and none of those vantage points is more central than any other. Our vantage point shows us the Great Attractor, Laniakea, the Shapley Concentration, the cosmic web extending in every direction. A hypothetical observer in a galaxy in the Shapley Concentration would look out from their own horizon and see a different arrangement of structures, our local group a faint concentration at 250 million light-years distance, the flow patterns of their own neighbourhood, organised around their own gravitational landmarks. Neither map is more correct. Both are partial. Maps have edges. The territory doesn't. This is still true. It was true at the beginning of this chapter and remains true now. Not resolved, not transcended, just acknowledged and left where it is, which is perhaps the only honest thing to do with a fact about the universe that the universe itself doesn't seem interested in resolving. The surveys will continue. The map will move its edge outward. What lies beyond the current edge will become in time part of the picture, and the edge will simply be somewhere else, further out, still moving. The next chapter turns inward, not to a smaller scale, but to the physics underneath all of this, the geometry of space-time that makes a structure like the Great Attractor possible at all. Every map has a border. Not because the thing being mapped ends there, but because the paper ends, or the screen ends, or the human attention that commissioned the map had a specific region in mind and stopped when that region was covered. The border is a practical decision, not a statement about the territory. It says, we were interested in this much, and no further, for now. Cosmological maps have the same feature and a different problem. The border of a cosmological map is not just a practical decision about how much to show, it is also, in some cases, a statement about what is accessible, what light has reached us, what instruments can detect, what time has allowed us to observe. The border is where the knowledge stops, not always where the territory stops. And in cosmology, those two things are not the same. Start small. The solar system. A map of the solar system has a practical edge somewhere beyond the orbit of Neptune, or beyond the heliopause where the solar wind gives way to interstellar space, or beyond the theoretical outer edge of the Oort cloud, where the sun's gravitational influence fades into something that can no longer be clearly distinguished from the general field of the galaxy. These are different edges at different distances for different purposes. The map you choose depends on what you're trying to show. Move outward. The galaxy. 100,000 light-years across. A disk with the bar at its centre and spiral arms trailing outward through the disk surrounded by a spherical halo of older stars and dark matter, extending perhaps 10 times the diameter of the visible disk. The map of the galaxy has edges in the practical sense and edges in the epistemic sense. Regions we know well because they are near enough to resolve individual stars. Regions we know less well because the dust of the disk obscures them. Regions at the outer halo where the boundary between galaxy and intergalactic space is genuinely diffuse. Move outward again, the local group, the Virgo cluster, Laniakea, the region of the Great Attractor, the Shapley Concentration. Each scale requires a different map, a different projection, a different choice of what to show and what to omit. No single map holds all of it in a way that is simultaneously accurate and comprehensible. The solar system on a map of Laniakea would be a point too small to represent, smaller than a single pixel at any resolution useful for showing the supercluster's structure. The supercluster on a map of the observable universe would itself be a small feature in a larger pattern. One knot in the cosmic web among thousands, the cosmic web. This is the name for the large-scale structure of the universe as a whole, the pattern of filaments and sheets and voids and nodes that the distribution of matter forms across the full observable volume. Galaxies are not distributed randomly. They are not even distributed uniformly. They trace a network, a foam-like structure, sometimes described of intersecting filaments along which galaxies and galaxy clusters are concentrated, surrounding vast empty regions called voids that contain relatively little matter and can span hundreds of millions of light-years across. The nodes of the cosmic web, where multiple filaments intersect, are where the largest mass concentrations sit. Galaxy clusters, superclusters. The Great Attractor region is one such node. The Shapley Concentration is another. There are hundreds of comparable structures within the observable universe, each one a knot in the web, each one the gravitational anchor for its local region of the flow field, each one pulling its nearby galaxies through the expansion the way the attractor pulls ours. The map of this structure, the cosmic web across the full observable universe, has been assembled over decades from successive redshift surveys, each one deeper and wider than the last, each one adding detail to a picture that became recognizable in its broad outlines in the 1980s and has been refined continuously since. The first clear image of the cosmic web emerged from the CFA redshift survey in 1986. The first slice of the universe mapped in 3 dimensions using galaxy redshifts as a proxy for distance, revealing a pattern of filaments and voids that nobody had quite expected to see so clearly. The Great Wall, a sheet of galaxies stretching across the survey slice, was the most prominent feature in that first map, an enormous structure whose discovery required only that someone measure the distances to enough galaxies in a large enough region of sky to see the pattern they formed. Subsequent surveys went deeper. The Sloan Digital Sky Survey mapped hundreds of millions of galaxies across a large fraction of the sky to much greater distances, producing a map of the cosmic web in sufficient detail to see its statistical properties clearly enough to compare with the predictions of cosmological models. The models, simulations of structure formation based on the physics of gravity, dark matter, dark energy and the initial conditions set at the moment of the Big Bang, reproduce the cosmic web with remarkable fidelity. The filaments, the voids, the nodes, the statistical distribution of structure across different scales. All of it emerges from the physics when the right initial conditions and the right cosmological parameters are put into the simulation. This agreement between observation and simulation is one of the strongest pieces of evidence that the standard cosmological model, the lambda CDM model, containing ordinary matter, dark matter, and dark energy in specific proportions, is at least a good approximation of how the universe actually works. And yet the map doesn't have an edge in the way that matters most. The observable universe has a horizon, a distance beyond which light has not had time to reach us since the universe became transparent, roughly 46 billion light-years away in every direction. But this horizon is not an edge of the universe. It is an edge of what we can currently observe. What lies beyond it is, in the standard cosmological picture, more universe, more structure, more filaments and voids and clusters. The cosmic web continuing beyond the horizon in a volume we cannot access because the light from it has not yet reached us. Whether that volume is finite or infinite, whether the universe beyond the horizon is structured similarly to the part we can see or differently, whether it has the same physical constants or others. These are questions that current cosmology cannot answer, and some of them may be questions that no observation will ever be able to answer, because the information needed to address them lies permanently beyond the horizon. The map stops at the horizon. The territory does not. This is the contradiction that sits quietly at the center of cosmological mapping, that the map is real, accurate within its domain, beautifully detailed in its better studied regions, and genuinely incomplete in a way that cannot be remedied by better instruments alone, because some of the incompleteness is not a matter of instrument sensitivity, but of the geometry of space-time and the finite speed of light. It seems, sitting with this, that cosmology is in the position of a cartographer who has mapped everything reachable and knows with certainty that the territory extends beyond the reach, but has no way of going there, no way of sending a probe, no way of receiving a signal. The edge of the map is the edge of the accessible, not the edge of the real, and within the accessible region, the map is still being made. New surveys, the dark energy spectroscopic instrument, the Euclid Space Telescope, the Vera Rubin Observatory, are extending the redshift surveys to greater depths and higher precision, adding detail to the cosmic web, measuring the distribution of structure across scales that previous surveys couldn't reach, testing the cosmological model against observations it hasn't yet been confronted with. Each survey will extend the map. None of them will reach the edge of the territory. The Great Attractor sits in the map. It is a node in the cosmic web, a local one, in cosmological terms, at 250 million light-years, well within the region that current surveys have characterized in considerable detail. It is not mysterious in the sense of being undetected or unmeasured. It is mysterious in the older sense, genuinely complex, incompletely resolved, embedded in a structure that extends beyond it in every direction into a universe whose full extent is not known. The flow that carries our galaxy toward it is a local expression of the same physics that organizes the cosmic web at every scale. Gravity pulling matter toward the overdense regions, the expansion of space pulling everything apart, the tension between them producing the structure we see, the filaments and voids and nodes that define where mass has gone, and where it hasn't, over the 13-odd billion years since the universe cooled enough for structure to begin forming. Our motion is one small thread in that pattern. The pattern is large enough that calling it large does nothing useful. Every map has a border. The cosmological map has one too, at the horizon, where the light runs out, where the accessible ends and the real continues into a volume that no instrument will ever survey, no probe will ever reach, no signal will ever return from. The map is accurate. The border is real. The territory beyond it is also real and continues, and has no known edge, and may not have one at all. That is where the map stops. It is not where the universe stops. The next chapter turns toward gravity itself, not as a background assumption, but as the thing that made all of this, at every scale possible. Gravity is the most familiar force in human experience, and the least understood at the deepest level, and these two facts coexist without one diminishing the other. The familiarity coming from a lifetime of contact with its effects, the objects that fall and the ground that holds and the weight that is always present in the body, and the depth of the mystery coming from something else entirely, from the way that gravity, when you follow it far enough into the mathematics, resists the unification that the other fundamental forces have gradually submitted to, remaining obstinately itself, described beautifully by general relativity at the scales we can test, and generating genuine theoretical difficulty at the scales where relativity and quantum mechanics are supposed to meet. That difficulty is not the subject of this chapter. This chapter stays at the scale where general relativity works, where it has been tested and confirmed, and where its predictions match observation with a precision that is, by any reasonable standard, extraordinary, and asks what gravity actually is at the scale of the Great Attractor, which is a different question from what gravity is at the scale of a falling apple, or an orbiting planet, or even a galaxy rotating around its center. General relativity describes gravity not as a force but as a geometry. Mass and energy and momentum and pressure, all of which contribute to the source term in Einstein's field equations, curves space-time, the four-dimensional fabric that combines the three dimensions of space with time into a single structure, and objects moving through that curved space-time follow the straightest possible paths available to them, which in a curved geometry are not straight lines but curves, and those curves are what we observe as the trajectories of falling objects, orbiting planets, bending light, and the large-scale flows of galaxies through the universe. The apple falls because the mass of the Earth has curved the space-time around it, and the apple, moving forward through time in the absence of any force to redirect it, follows the straightest path available in that curved geometry, and that path leads downward. The Moon orbits because the Earth's mass has curved space-time in a way that makes a closed path around the Earth the straightest available trajectory for an object moving at orbital velocity. The galaxy falls toward the Great Attractor because the mass of the attractor region has curved space-time across 250 million light-years, and the galaxy, moving through that curved space-time under no propulsive force, follows the path that the geometry offers it. The physics is the same in all three cases. The scale is not. At the scale of the Great Attractor, what does it mean for mass to curve space-time? The curvature is real, measurable in principle, through its effects on the trajectories of galaxies and the distribution of matter and the statistical properties of the cosmic microwave background on large angular scales. But it is extraordinarily gentle at any given point in the intervening space, because the mass, though enormous in aggregate, is distributed across an enormous volume, and the local curvature at any specific location between here and the attractor is very small. The gradient of the gravitational field, the rate at which the strength of the pull changes with distance, is what accelerates objects, and across the vast distance between our galaxy and the attractor, this gradient is so shallow that its direct effect on any localized object is imperceptible. And yet the integrated effect, the cumulative result of that shallow gradient acting on our galaxy across the full distance over the full span of time, is 600 kilometers per second of peculiar velocity, directed toward the attractor, built up over billions of years of continuous acceleration so gentle that at any given moment it would register nowhere in any instrument sensitive only to local conditions. This is how gravity works at this scale, not as a sudden force but as a patient geometry, bending trajectories by amounts too small to see in any short interval but compounding those bends over time into velocities that are, by the time you measure them, substantial. The word curvature invites a visual metaphor. The stretched rubber sheet, the bowling ball pressing down into a membrane, the depression in the fabric, and the metaphor is useful for a moment and then starts to mislead, because the rubber sheet is two-dimensional and space-time is four-dimensional, and the bowling ball appears to curve the sheet by pressing into a third dimension that the sheet doesn't have, which has no analogue in the actual physics, where space-time curves without curving into anything outside of itself, intrinsically, in a way that has no visual representation because nothing in human experience is intrinsically curved in four dimensions. The mathematics is precise. The picture fails. It seems better at this scale to let the mathematics be the picture, to hold the word curvature as pointing at something real and quantifiable without trying to visualize it in a way that requires a dimension that isn't there, and to work instead from the consequences, which are visible, the galaxies moving, the flow coherent, the attractor sitting at the gravitational center of a supercluster, because that is where the curvature, integrated across the entire structure, reaches its local minimum, the deepest point in the geometry of a region of spacetime 500 million light-years across. At the scale of the solar system, general relativistic effects are small corrections to the Newtonian picture, important for precision, necessary for GPS satellites and the perihelion precession of Mercury and the bending of starlight around the Sun, but small enough that Newtonian gravity gives a good first approximation for most purposes. At the scale of a galaxy, relativistic effects are more significant. The rotation curves of galaxies, the bending of light by galaxy clusters acting as gravitational lenses, the dynamics of stars near the supermassive black holes at galactic centers, all of these require the full relativistic treatment to describe correctly. At the scale of the Great Attractor, the relevant physics is cosmological, the same general relativity, but applied in the context of an expanding universe, where the background spacetime is not flat and static but curved and dynamic. The expansion itself a solution to Einstein's field equations applied to a homogeneous and isotropic universe filled with matter and energy. The peculiar velocities, the motions of galaxies relative to the expanding background, are superimposed on this dynamic background, and the relationship between those velocities and the mass distributions that source them is described by the equations of linear perturbation theory, an approximation to general relativity that works well when the density fluctuations are small relative to the background, which they are on the largest scales even though they are not on the scales of individual galaxies and clusters. This is the theoretical framework within which the mass of the Great Attractor is estimated from the observed peculiar velocities, not a simple application of Newton's law of gravitation, though the results are not dramatically different from what Newton's law would give in this regime, but a careful calculation within a relativistic expanding universe, using the full machinery of modern cosmological perturbation theory. There is something almost counterintuitive about the fact that the largest gravitational structures in the universe are, locally, the most gentle, that the curvature sourced by a mass concentration of 100,000 galaxies is, at any given point in the space between us and it, less extreme than the curvature near a neutron star or near the supermassive black hole at the center of our galaxy, or even near the surface of the Earth. And yet the large-scale structure is in some sense more consequential for our motion, because it acts over distances and timescales that the local, intense curvatures cannot. The gravity of the ground beneath you is stronger, locally, than the gravity of the Great Attractor by many orders of magnitude. The gravity of the Great Attractor has been shaping the trajectory of our galaxy for longer than the Earth has existed. Both things are true, and it takes a moment, maybe more than a moment, to hold them together without one cancelling the other, the local intensity and the cosmic patience of the same force operating at scales that don't naturally sit in the same thought. Gravity at the scale of the Great Attractor is not a different force from the gravity that holds you to the floor. It is the same geometry, described by the same equations, sourced by the same relationship between mass and the curvature of space-time, operating at a scale where the numbers are so large that the intuitions built from ordinary experience provide almost no guidance. The equations scale. The intuitions don't. What remains when the intuitions are set aside is the mathematics, and the mathematics says that the mass of 100,000 galaxies, distributed across a volume of space 500 million light-years across, curves the space-time within and around that volume in ways that are small locally and enormous in aggregate, and that any galaxy unfortunate enough, or fortunate enough depending on how you hold it, to be within that curved region will follow the geometry, will move in the direction that the curvature slopes toward, will accelerate gently over billions of years toward the gravitational minimum of the structure. We are that galaxy, The curvature is the reason. The next chapter is the last one, and it is quieter than this. The motion is happening right now, not as a thought experiment, not as a conclusion drawn from data in a paper you might one day read, as a physical event, occurring in the same moment that you are lying still, in the same moment that your breathing has slowed and the room has gone quiet and whatever occupied your mind earlier tonight has mostly released its hold. The galaxy is moving. You are moving with it. There is a particular quality to the end of something, a conversation, a long day, a chapter, where the mind doesn't want more information, doesn't want the next thing, but wants instead to rest with what is already there, to let what has been said settle without adding to it. And this chapter is aware of that quality and is trying to honour it rather than work against it. So there will be no new physics here, no new surveys, no new estimates, no new structures introduced in the final pages that require the mind to reconfigure what came before, just the motion, which was always the subject. You've been moving toward the Great Attractor for your entire life. Every moment you have ever experienced, every morning, every hour of sleep, every unremarkable Tuesday and every significant day has taken place inside a galaxy moving at 600 kilometers per second toward a gravitational center 250 million light years away, hidden behind a curtain of dust that our instruments have only partially penetrated, embedded in a supercluster of 100,000 galaxies whose boundary is defined by the direction that all of them, including this one, are falling. That motion was happening before you were born. It was happening before any human was born. It was happening before the first living thing on this planet processed energy from the sun and reproduced, and began the long chain of contingent events that eventually produced, among other things, the capacity to lie in the dark and think about where everything is going. The stars outside tonight, the ones visible through whatever window or wall or atmosphere separates you from them, are inside this motion. Every one of them is a member of the Milky Way, which means every one of them is being carried toward the attractor in the same flow, at the same velocity, along the same curved path through the space-time that the attractor's mass has shaped over billions of years. The stars don't know this. The knowing belongs to a very recent and very local phenomenon, the development, on one small planet orbiting one ordinary star in one outer spiral arm of one galaxy, among 100,000 in a supercluster, of the capacity to measure velocity fields and read redshifts and infer mass from the motion of galaxies that are themselves too far away to resolve individually in most instruments. The knowing is new, the motion is old, 600 kilometers per second. In the time it takes to read that sentence, the galaxy has moved roughly 2,000 kilometers in the direction of Centaurus. In the time it takes to fall asleep, 20 minutes perhaps, if tonight goes easily, the galaxy will have moved something in the range of 720,000 kilometers toward the attractor. In the time it takes to sleep through a full night, 8 hours, the galaxy will have moved approximately 17 million kilometers. None of this changes anything about the night. The room is the same temperature. The weight of the blanket is the same. The darkness outside is the same darkness. The motion doesn't announce itself. It never has. There is a question that has been sitting at the edge of this chapter since it began, whether the motion matters, whether it means something, whether the fact of being carried through space toward a hidden gravitational center at 600 kilometers per second has any bearing on the experience of being alive on a small planet in one corner of the structure doing the moving. The honest answer is probably that it doesn't, in the direct sense. The motion is too large and too slow to touch the scale at which human life actually occurs, too far removed from the conditions that determine whether a day goes well or badly, or whether the people you care about are all right, and yet it seems worth knowing. Not because it changes anything, because it is true. The Great Attractor will not be reached in all probability. The expansion of space is likely to keep the distance from closing in any time frame that the word arrival can accommodate, the geometry working against the motion in the way that the previous chapters described. But the motion continues. The falling continues. The 600 kilometers per second is a real velocity that the galaxy carries right now, and will carry tomorrow, and will carry while the Sun completes another of its 230 million year orbits around the galactic center, indifferent to whether anyone on any of the planets accompanying it is aware of it. The indifference is not hostility. It is simply the nature of physics at this scale, vast, passionate, operating on timescales and distances that have no natural relationship to the timescale of a human life, and yet somehow including that life, carrying it, moving it through space towards something hidden at the same velocity as every star in the galaxy, and every galaxy in the supercluster. All of it together, all of it still. This is where the script ends. Not because the subject is finished. The subject is not finished. The surveys are ongoing. The models are still being refined. The zone of avoidance still partially obscures the gravitational center of the structure we live inside. And there will be papers published next year that improve on the estimates this script has described and possibly revise some of them in ways that matter. The subject continues. The motion continues. But the night is late, and the mind is close to the edge of sleep, and what remains after 16 chapters is not more information, but simply this. The galaxy is moving, has been moving, is moving right now, and you are inside it, still and moving at once, carried towards something enormous and hidden and real, in the company of 100,000 other galaxies doing the same thing. In a universe so large that this entire motion, the whole of Laniakea falling toward its gravitational center, is one small feature in a pattern that extends in every direction to a horizon beyond which we cannot see. You are inside that pattern. You've always been inside it. If this is the kind of space that helps your mind go quiet, if spending time with physics at this scale is something that works for you at the end of the day, the channel page is there when you want it, and there may be a way to be part of what keeps it going if that's something you'd like to explore. But that's for another night. For now, the motion is enough. The galaxy is still moving. You can rest.